Welcome to comparing strong acids and weak acids. In this animation, we will see what happens when a strong acid, any strong acid, right? So it says HX is dissolved in water. We're going to assume that it's a solid to begin with. There's a couple of strong different acids that we have here. We have HCl, we have HBr, HI, HNO3, etc. So there's a whole bunch of strong acids. Those are some of the most common ones listed down below. But a strong acid is one which reacts completely with water, 100% with water, and it produces hydronium ions. In other words, the strong acid is fully deprotonated into the water. And so the reaction that shows there is HX is aqueous, so it's going to dissolve or split apart in water. When you add it to liquid water, it turns into a hydronium ion. And so if I go ahead and replace HX with HCl, for example, because HCl is one of our strong acids, if I add this to water, some of this hydrogen right here is actually going to go ahead and go over to the water, right? This hydrogen right here is going to go to the water. And when it goes to the water, it creates hydronium, which is H3O+, and then chloride ion, which just kind of disappears into the solution, right? It stays dissolved into the solution. The other way you could write it, if it's a strong acid, your strong acids are aqueous. And if it's aqueous, it means it dissolves 100% in water. And so it's going to split apart into the hydrogen plus the chlorine atom, or whatever the anion might be. So it could be nitrate, iodide, bromide, depending on your strong acid, right? And so these guys right here, when it says, let me change my color, when it has H3O+ and H+, hydronium and hydrogen ion, those are the same thing. They mean the same exact thing. And so if we go ahead and run the simulation over to the left, once the HX is immersed in water, it will begin to dissolve, and because it's a strong acid, it will dissociate to form hydrogen or hydronium and the anion. And depending on the ratio, usually it's a 1-to-1 ratio. If we had sulfuric acid, H2SO4, it would be a 2-to-1 ratio because we need 2 hydrogens or 2 hydroniums for every one of the sulfate. So that's strong acids. They dissolve 100% in water. All right, let's go ahead and look at a weak acid. And the only difference between a strong and a weak acid is that your weak acid is going to actually create less dissociation. And so it's going to still do the same thing, but the way we determine that is with an arrow. So we just include a little arrow. And so say we have hydrofluoric acid. Hydrofluoric acid is a weak acid, and we add it to water. It's still going to do the same thing where it went ahead and it donated that hydrogen over to water, but it's not going to do it the same amount, right? It's going to dissociate less or almost not at all. So the way we show that is we do back and forth arrows. They're called equilibrium arrows. So one goes forward, one goes backwards. And so then we have hydronium, H3O+, and our anion, in this case it's fluoride. And again, if you wanted to, you could show it as hydrogen and fluoride, your cation and your anion. The arrows would do the same thing, where you have hydrofluoric acid, HF, splitting apart into the hydrogen positive and the fluoride negative. But again, it's a weak acid, so it's not going to dissociate a whole bunch. It usually dissociates less than 5% on average. And so that back and forth arrow shows us the dynamic between the HF and the H+ and the F-. The other way you can kind of visualize it is a weak acid tends to stay intact, and so it likes to be on this side, whereas it dissolves but not as much. So if I draw it tinier, it kind of shows you a visual representation of how much dissolves versus how much stays intact. And so let's go ahead and look at the animation. So once the HA the weak acid is immersed in the water, it will begin to dissolve. Because it is a weak acid, only a small fraction of it will dissolve or dissociate into the water. So the majority of the weak acid molecules remain in their molecular undissociated or undissolved form. This is why we represent weak acids in an aqueous solution and the reactions as HA molecules. The acid and its conjugate base, the A-, the anion, exist in dynamic equilibrium. So they go back and forth. So they can recombine, and they can recombine to form the weak acid again, whereas the other weak acid molecules dissociate to form the hydronium and the anion. Right, so when a hydronium and an anion come in close contact with each other, then they're going to go ahead and recombine into the weak acid. And vice versa, if you have a weak acid, eventually it could dissociate. There we go. All right. So note that the ratio of hydronium and the anion to the weak acid is constant, meaning that the equilibrium constant for the process is represented by the equation, where the equilibrium constant is the reactants divided by your product. Or sorry, I messed that up. The product, right? Your H3O plus and A minus are your product. So those are on the top of your fraction, and then it's divided by your reactant, and it's your weak acid on the bottom. Hopes this helps. Ask questions if you have any questions.